get started. It's my pleasure to introduce Li-Hong Xu. Li-Hong is a professor from the University of New Brunswick. She's currently spending part of her sabbatical here in Toronto. She's been for a week and a half now down in the physics department on the 6th floor. And she's going to stay until the end of the week and come back from February 20th to March.
Good memory.
Li-Hong works on molecular spectroscopy, mostly in a laboratory setting, I think.
That's right.
But today she's going to tell us what ALMA can tell us about molecules out in the some medium. Please.
Thank you, Neil, for the introduction. And I first must express my sincere gratitude to have the opportunity to actually spend a little time here. Previously, I've been always travel back and forth, maximum like 2 days in Toronto area, but this time extensive stay, and I really feel the dynamics here. So far, I really enjoyed every minute I stay here. It's so much going on. And also for the opportunity to share some of our recent results with you. So today I'm going to talk about exploring molecular complexity in the age of ALMA. And I hope this talk for all of you, perhaps there are some parts you're familiar with and other parts you're not so familiar with. But my real hope is there's always a part, potentially, of some interest to you. So more specifically, we're going to look at the high angular resolution of the ALMA, take advantage of the ALMA, and for the observation in the 3 millimeter wave region, more specifically look at 2 series of molecules, alkyl series as well as the one with sulfur substitute in this unit. So basically, the smallest unit for alkyl is methyl alcohol. And then when you can replace one of those R with another methyl group, then the molecule size gets bigger. So you have a methanol, ethanol, and propanol, etc. And you have the equivalent of sulfur companion parts. On our team, we have our colleagues in the Maxwell Planck Institute for Radio Astronomy, and as well as we have astrochemists in University of Virginia, and myself, as Neil mentioned, is the laboratory molecular spectroscopist. We supply the data, and we have in between person my colleague from University of Cologne. We often go there and travel to get our measurements. So I will show you some result. This is 3 years old from the 30-meter single dish telescope in the millimeter wave range, and then telling you, although we had some discoveries there, but in the end, our further analysis was hampered by the confusion limit. And then we took advantage of ALMA with higher angular resolution and have made latest new discovery, which we were very happy about it. A few words about the motivation. The molecular complexity in star-forming regions is an important aspect of chemistry, and because organic molecules and formed in the interstellar environment and may have contributed to the formation of the life on the Earth and possibly in other planets. So when we look for the origin of life, the ultimate goal is to find a species has amino acid units, which contains the amino group as well as carboxyl group. The simplest amino acid is where you replace this R with just one hydrogen. That's glycine. The glycine molecules so far has not conclusively observed in the interstellar environment, but has been observed, as I will show you later on, from the sample brought from comets. Although glycine hasn't been formally conclusively confirmed, other units could lead towards that unit, such as the propionocyanide and ethyl format, as well as amino acetyl nitrate, has recently been observed in the SAGB2 north and the central units. It's commonly known now, the SAGB2 and the middle part. Let's see if we can stop here.
You need to pull it sideways a bit.
Sideways?
experiment.
Yeah. Have turned to be the best hunting ground for the complex organic molecules in the interstellar medium. A question and a few possible answers. Did interstellar chemistry contribute to the formation of the life on Earth and other planets? So far, there's more than 80 amino acids has been found in the meteorites on Earth, and isotopic and ceramic composition suggest their extraterrestrial origin. As I mentioned, the glycine, although hasn't been conclusively confirmed in the interstellar detection, but has been formally confirmed in the detection of the sample brought back from a few years ago, NASA's Stardust spacecraft solar system exploration launched in 2006, and this paper was published just a few years after. Most recently detected species all suggest the evolution of this to the traces of specific chemical and physical conditions, possibly in the space. So a few words about SHB2. It's a giant molecular cloud. It's very near the center of our Milky Way. And the density of the cloud is extremely dense. That's in favor of forming the complex organic molecules. Divides into three cores, the north and middle and the south. And in this work, we are looking at the north cores. Okay? And both middle and the north are considered as very active site for the new star formation area. The temperature range, depending on whether you're looking at the surrounding envelope or the dense star forming regions, ranging from 40 Kelvin up to 300 Kelvin. And the complex contains the cold dust consisting of a silicon core and surrounded by water, ice, and carbons. The high current density really in favor of the complex molecule, which we are interested in. The typical compact molecule has a very rich spectrum in this wavelength region, about 100 to 1,000 micrometer, translates into frequency is about 300 gigahertz to 3 terahertz region. That's the region of ALMA where the complex molecule has a very rich spectrum there. According to the Cologne database for molecules in space, in fact, about half of all the known interstellar molecules so far were first found near the SHB2. And since then, nearly every other currently known molecules has been detected in this feature, okay, has detected in feature. As I mentioned, according to the Cologne database for molecule in space, this is a year-old update. So far, there's more than 180 species has been detected, the size ranging from 2 to 12. There are a few big ones, and including the bulky ball C60 and the C70. The molecules in the extragalactic environment, this database is not as abundant as the one in the ISM. For those of you who have used the database, you will see, first thing you see is a table like this, arranged according to the column and going up in size. So the goal is you keep finding new things and update it here. Now, once you find a new species, then the astronomers will consider the species as the weight, because you got to weight the interstellar garden before you can find the new species. Okay? I have a few circles here. Let me just point out, first of all, I want you to sort of remember this. Here it says out of this table, 180 here and about 56 here, known species in the interstellar environment or the extragalactic environment. Apart from the bulky ball, rest of them all have this straight chain structure, except our most recent finding, observe the branched structure. So that's a quite big deal, which I will point out towards the end of my talk. And so instead of just seeing the chain molecule, now we have observed branched molecule. So as I mentioned in this talk, we're going to focus on the methyl alcohol, ethanol, and keep going propanol here, as well as we have the mercaptan, and then the ethyl mercaptan haven't put into this database just yet. Of course, once you weigh the molecule, we find a new species, which is now called interstellar flower. And the next thing is try to understand where those things come from, how do they come from. So how do complex organic molecules form in the interstellar environment? Now my colleague tells me the gas phase ion molecule reactions ineffective, the grain surface chemistry at a low temperature not sufficient, and you really need a radical reaction upon warm up is required. So all those that, in order to test the model or to improve the model, the new data is needed. And to test the prediction, you need to put new molecules into the whatever the model you're talking about. So this is the really interplay between the observational chemistry, which is my colleague's job, and myself, laboratory spectroscopy, and then the astrochemist or astrophysicist. Our job description, the astronomers will do the line survey or targeted scan. Myself will do the laboratory spectroscopy and identify the molecules, fit to the model, and generate a line list so that the survey spectrum can be interpreted or feed into the database. And from that, we're going to try to understand the formation of complex molecules. And this particular work, which just appeared online, haven't appeared in hard copy yet, focus on understanding the sulfur chemistry in the dense interstellar medium environment. So this gives me the opportunity to mention about those two classes of molecules, few words about the basics. The molecule on the left-hand side, methyl alcohol, and then ethanol and propanol, as well as the one on the left-hand side, replace the oxygen to the sulfur. All those molecules have one thing in common. That you can sort of think about here this molecule as two parts, and they can do internal rotation with respect to this bond, do this twisting motion. That's called the large amplitude motion. And this motion, in fact, doesn't need too much energy. So it's quite floppy. We call quite floppy because the force constant is very small. It's this large amplitude motion basically results in the rich spectrum and complex spectrum and brings a challenge to us. And we look at not only their parent species as well as other isotopic forms, which also can be detected in the interstellar environment. So I'm going to now give you a few slides of the basics about basic crash course about the large amplitude motion in the torsional spectrum. When we want to detect the molecules, since the molecule has the torsional motion, you can think about extension of the framework or extension to the methyl top. In either case, in this case, I start from methanol, you go into acetaldehyde, acetic acid, etc. So you can grow the framework. All those molecules has dipole moment, which is a good thing because once you have a permanent dipole moment, you can observe the rotational spectrum listed here. As well as I said, those complex molecules has this twisting motion. And so the twist motion, we can define a parameter called the rho. This parameter is the moment of inertia of one part of the molecule divided by moment of inertia of the whole thing. So as the species going up, either increasing in size of the framework or increasing size of the top, then this rho factor decreases quite rapidly. The implication for that is as this molecule doing the twisting motion and induce the dipole moment perpendicular to the twisting motion here, and that in fact is proportional to the intensity of the torsional spectrum in the terahertz region, in the terahertz region. So this led me to tell you, basically, trust me, when you go in to study big molecules, there's challenge because the spectrum is very weak. It's very difficult to detect. Okay? You need a sensitive technique. And here's illustration. If you're going down rho by a factor of 10, and intensity drops down 100 because intensity goes by the rho squared. Okay? So that says studying big molecules is challenging because the spectrum is weak. You need the more sensitive detection. But it's also the plus part too. That is the second basics I want to tell you. The molecule we are interested in all have equivalent 3 hydrogen in the bottom. That's called the methyl top. So in other words, potential has 3-fold here. So the torsional energy can be expressed as 120 degree and then multiplied by this rho factor, and the K is the rotational quantum number of J projection onto the symmetry axis. So the torsional energy is plotted like this. It's a cosine function, basically, cosine function. But because of this rho factor, the big molecule, the smaller rho value, in fact, gives you more sample points on the potential here. So theoretically, once you get a spectrum, the heavy molecule is more easy to model compared with the light molecule, because the light molecule, you don't get too many sampling points on the potential. Okay? That's the second basics I want to tell you. So the certain advantage to study big molecule, theoretically speaking, as well. The third basics I want to tell you is when we turn on the rotation, the J is the overall rotation quantum number, and the K is the projection of the J onto the molecular axis. The expression, the rotational energy, is a function of JJ plus 1 and the K squared. So when we look at rotational-less molecule, in other words, K equals to 0, then this is the barrier to internal rotation. So in other words, you can think about the framework passing one hydrogen, passing another hydrogen, and 3-fold. Okay, 3-fold. When we not look at the rotation, then you have different torsional level. The lowest torsional level is basically below the barrier, and because this internal rotation is quite floppy and takes not much effort going through another barrier height, so the first excited torsional state is just straddles the barrier top, and you have second, you have third, and fourth, etc. Okay? And in fact, in the decent temperature, there is still sufficient population here. In other words, you can get the spectrum. Okay. Now, when we turn on the rotation here, we just turn on the K, now you can see those levels. Okay? Now, I hope you agree with me. The levels doesn't seem at first glance have any regularity there. Okay? So this means the spectrum, torsional spectrum in the tetrahedral region, first of all, it's very rich because the lines are so close together. And second of all, transitions are really everywhere. And the third thing I want to point out is because, by the way, different color coding, this is the ground torsion, and then the burgundy here is the first excited, the green one is second, and then the higher you go, the spray gets bigger. This means there's no direct correspondence between the frequency to the quantum number we are dealing with. Suppose we say we stop at the energy of a 400 wave number, and already there covers not only ground at first and the second. If you're going up, then there's more states is going to be involved. Okay, more states is involved. So really, when you go up in frequency, I always afraid to look at extrapolation because in order to predict this area, well, you really have to include everything. For that reason, we often, or myself, often have a little bit of friction with my astronomy colleagues because the astronomers, they want everything, the database. They want everything yesterday, not tomorrow. Okay? They are very impatient. And because the new telescopes and the space observatories are online, and they can detect much warmer temperature and go higher frequencies, and to us, this correspondingly to go to the higher rotational and torsional quantum states. You got to deal with more states. Okay, and so in other words, when I generate a line list, I'm always afraid of somebody to look at it too carefully because I know extrapolation is very dangerous in the molecule we are dealing with because it's complexity of this torsion motion. So experimentally, what we have to do is, because we want to increase in reliability of the prediction of the database, we want to, first of all, get the data experimentally as broad coverage as we can. So we basically try to go any instrument, either home build or any way we can have put hands on, access it, going from microwave all the way up to the terahertz region. Sometimes we have to go to infrared region as well. Different spectrometer here. We have close collaboration with University of Cologne, as well as our JPL colleagues in NASA. And in the microwave region, we use direct synthesizer, and then going up. Recently, we are in fact quite comfortable to access terahertz region using the Virginia diodes, plus amplified the multiply chains. And those diodes are really wonderful plus chains. You just multiply 72 times or 108 times. And in fact, the JPL's instrument, they use the components left over, test instrument from the Hi-Fi for the Herschel space mission, and they can get to 162 multiplies. So almost gets to the 3 terahertz region. And we also are constant user of the synchrotron radiation, except the synchrotron radiation in terms of the precision-wise is not as good as those guys, but it gets really easy coverage. We study not only mainly species, but also other species, and we replace the carbon to the 13, and we also replace the oxygen to the sulfur, and most recently, in fact, we are just doing the chemistry, try to replace the carbon to the silicon. We want to look at the silicon-based chemistry as well. We do line-by-line survey, as well as do the broadband scan. And that's the typical accuracy we're talking about. Experimentally, we measure best we can, and then come to the theoretically, we want to reproduce the line to this accuracy, and then generate a line list. So fundamentally, what we want to ultimately understand is the molecular structure and tunneling dynamics. And once we get the spectrum, we have line position and the line intensity, and then we perform the quantum assignment, attach a quantum number. From there, we reconstruct the observed energy structure, and then we feed into quantum mechanics Hamiltonian and fit the position and the intensity. And with that, our parameter of the eigenvalue and eigenfunction allow us to generate the spectrum at other temperature and pressure condition. And those are the line lists we produce. So that loop, the cycle we are going through, recently have a renewed interest even for some really well-known molecules, simply because, as I mentioned at the early beginning, there's new telescopes that they can cover more regions and at increased resolution. And our line list finally feeds into the Hytron and the Cologne database for molecule in space. So now let me show you the 3-year-old, the single dish 30-meter survey for SEG-B2. The first survey we did is about 36 gigahertz window. We retrieved, based on the greater than 4 sigma of signal to noise ratio, is about 3,700 lines. This translates to overall, it's 100 lines per gigahertz, which is zoned in on the top here. So that's 1 gigahertz. And you can see the line density there, okay, line density there. And we assigned about 70% of them. In other words, there's still 30% unknown for one or the other reason. Either the database is not complete, or the lines are just reaching the confusion limit. Out of 30% identified species, that belongs to 56 molecules, and then 66 minor isotope locks, and 59 vibrational excited states. Now, this statistics really tells you the sensitivity of that survey. It's pretty good, pretty good. You can detect all those vibration excited states as well as minor isotope locks. And that work was published a few years ago. The highlights of the 30-meter survey was, for first time, we observed those fairly big species. We consider they contain units of the glycine. okay, like amino acetonitrile, SO format, and also the propionyl cyanide. Unfortunately, according to the quantum chemistry calculation, we know for the propene cyanide, it has not only normal species, which is the chain structure, but also has a branched structure. But we couldn't detect in the 30-meter survey simply because the spectrum reaching its confusion limit. The lines are so dense, and the isoform would be a little bit less abundant than this. So this led us to turn to the ALMA. So we explored the molecule complexity using the ALMA instrument. That equation, everybody knows that. The angular resolution of an instrument is to do with the wavelength and then also dish size. So for 30-meter telescope, at 3 millimeter wavelength, the angular resolution is about 25. That was the spectrum I showed you earlier. So if we want to increase in the angular resolution to, say, 500 times at still same wavelengths, then you basically need a giant telescope. You need a huge telescope. And that is, in fact, achieved in ALMA by building a bunch of smaller telescopes, forming an array like this. Okay? So in the case of ALMA, there's 66 of antennas, and then works electronically, all has to be synchronized and in high precision. ALMA has 10 bands and covers from 30 gigahertz to 1 terahertz. In our work, we use the band 2 and band 3, and that's the frequency coverage we are using. Okay? And displayed here, showing in each band there's different tunings. Okay, it's about 5 tunings. In our cycle 0, we scanned the survey from 84 to 110 gigahertz at a much, much higher angular resolution than 25 from previous single dish scan. I will soon show you the comparison. And then we really want to confirm something, so we applied more telescope time. That's cycle 1, and we extended to 114 gigahertz. The angular resolution now is about 1.8 to 1.4, so that's about 20 times better than the previous 30-meter single-dish survey. So this is a comparison. On the top, we have the 30-meter survey. The angular resolution is about 27 here. The bottom, same core with ALMA in this case, there's some improvement here. But when we further zoomed in, looked at, instead of the 2 cores together, we separated the north 1 and the north 2, and now you really see the advantages of ALMA spectrum compared with the 30-meter single-dish scan. Especially in the second core, the lines are significantly narrower, and there very little confusion for identification of the species. And that led us, in fact, detected the isoform of the species we're looking for. It's in the branch form. So now I want to show you some ALMA spectrum for this series of molecules. So it's alkynyl series, starts from methanol, ethanol, and the propanol, and I also have 2 forms. And as I said, I haven't showed you yet, but believe me, I'm going to show you through the ALMA survey, we have identified the isoform, which is the branched form. The simplest alkynyl is a methyl alcohol. Methyl alcohol has been detected in the interstellar environment for more than half century now, so that's not a big deal anymore. Okay? Unfortunately, because the spectrum is so rich, so dense, now it has this name called the #1 interstellar weights. Okay? And everybody hates it. But to fully get rid of it, it's going to take another few years for the line list to be improved. And now ever since then, there's other isotopic forms of methanol has been detected in the SEG-B2 shortly after that. And in fact, the C13 form, in fact, is quite favored by my colleagues, astronomers, because the C13 form, first of all, is quite abundant, but second of all, it's not as abundant as the normal species. So those lines are all saturated, but those lines are not. So in fact, the C13 species now becomes a very good diagnostic tools for often to do the proper column density calculation. So showing here are some ALMA spectrum, survey spectrum. 3 colors here in black, in red, and in green. The blacks are observed. The green one is our current best fit with the new molecules we have put it in, use the LTE model. And the red one is a contribution of methyl alcohol for V0 only, in other words, ground torsional state only. And I hope you agree with me, see, overall, most of the big ones, which is strong ones, are all coming from methyl alcohol's contribution of VT equals to 1, okay? 0. Next, as I showed you earlier on VT equal to 0 below the barrier, 1 is straddles the barrier height, and then 2 and 3, and they are all there. Here, this is the VT equal to 1, red, contribution of methyl alcohol. That's the 2. And even up to 3 is still there. So no wonder it gets the name of most offensive ways at the moment, the number 1, okay? And other isotopic forms, this is the C13 VT equals to 1 in red, and the C13 of VT equals to 1 in red. And they are there. They are there. Okay, it's very, very abundant. Oxygen 18 is there as well. And I can keep giving you this CH3OD, different forms. And we are in the process of now looking for those 2 combinations, C13 and oxygen 18, in order to identify the isotopic ratios. From that, we can do population plot. Plotted on the vertical axis is the natural log of the Boltzmann factor. And the horizontal axis is energy divided by Boltzmann constant, K here. And therefore, the slope gives you inverse of the rotational temperature with minus sign in front. Okay? And so such information we can derive from the survey spectrum. And we have similar result for ethanol and propanol, but I'm not going to show all those things to you. But what I like to do is now move into the sulfur series. So we can replace the oxygen with sulfur, and so you have mercaptan, you have ethyl, mercaptan, and then keep going. And we have now, in fact, observed them in the ALMA spectrum. And mercaptan was never be observed up until 2-3 years ago. Okay? So you have VT equals to 0 of mercaptan and VT equals to 1 over mercaptan. That's the red curves here. And we have ethyl mercaptan listed here as well now. Okay? And with those new detections, those sulfur component new detection, we now, my astrochemist colleague now can put into his model and to generate the latest prediction. Now, the last few minutes I would like to do is to talk a little bit more about the so-called the straight chain versus branched business. So for the propanol cyanide, it's known there's 2 forms, normal form and iso form. According to quantum chemistry calculation, the normal form have 2 conformers. You have gauche and anti, and with gauche is a little bit low in energy. And those 2 forms, in fact, has all been detected from our 30-meter survey. That was 3 years old. For the first time, this is about a year old now, we have reported the detection of the isoform for this species from the ALMA survey. And I'm going to just put this here, says this is not a small deal, and for the reason I will soon indicate to you, tell you. We have, in fact, altogether detected more than 50 lines of isoform, more than 120 lines of normal form. So, this is more than a handful. In other words, the detection is quite firm. Okay, so cannot be random coincidence. So we believe we have conclusively identified or detected the isoform of this species in the ALMA spectrum of SEGB2 in the second North core. From that, we can similarly do the population plot and determine the temperature. Rotational temperature is about 150 Kelvin with emission size of about 1. And that work was published 2 years ago in the Science magazine. From our work, we can detect the ratio between the isoform versus the normal form, and that's about 0.4 to 1 to the 1. And the end of our work, we identified all new species. Then my colleague put into his model and improved his model. His model now tells us the ratio between isoform and normal form is about 0.375 to 1. So the agreement is really quite good. Okay, quite good. And based on the latest model, the formation on the grain surface, he proposed the pathway for forming the normal propionyl cyanide as well as the isoform. In fact, the two pathways are quite different. Okay, and so that's the pathway to form the normal form, and this would be for the isoform. It's quite different. So as I mentioned a few times now, the branched molecules in the interstellar molecules, this is a detection of that is not a small deal. The reason for that is as following. Was predicted back about the 1980, the branched species has to exist in interstellar environment. But it's only up here recent, which is the last year, was first conclusively observed or detected in the interstellar environment. So that's one thing we think this is not a small deal. But more importantly, the amino acids, as I mentioned earlier, there's more than 80 amino acids has been detected in the meteoroids. And they, in fact, all have this branched form. Okay? So we think we are one step more closer to hopefully, in the end, is going to detect the amino acid in the interstellar environment. That's the second reason we think this is not a small deal. So as I highlight here in red, based on our work, the detection of the isoform, which is the branched form, plus the best LTE model with the inclusion of every new molecules we have observed in those two series, really bodes well for the presence of more complex molecules in the interstellar medium, and hopefully it's amino acid, which is the ultimate thing we want to detect. So this just says the exploring the molecule complexity in the age of ALMA is only at the infancy, only starting. Okay, and the more survey has to be done, but the backbone of that just means there's more laboratory high-resolution spectroscopy has to be done first before you can interpret the survey spectrum. Okay, so with that, I would like to thank you for your attention and take any question you may have.
So can you learn something from the presence of specific molecules about the properties that the molecular cloud has, where you find them?
Molecular?
That molecular cloud has on largest astrophysical scale.
So you're challenging me here. I mentioned about, in our team, I'm the molecular spectroscopist, right? So I know, to be honest, I know very little about the astrochemical side, and yeah.
I think they have been used to trace turbulence in the cloud at some point. I don't remember quite the details, but they can be used for as tracers of temperature and structure in the clouds.
Yeah, I'm sure there's some new information can be learned that, yeah.
Have you measured the have you detected CH3D?
CH3OD? Yeah. I didn't show you. It's there. We also, in fact, we have measured the CH3OD, CD3OD, like folate deuterated, as yeah.
So have you measured CH3OD over CH3OH ratio? So the deuteration ratio is CH3OH.
So what you're saying is symmetric versus asymmetric. Is that the mesotopic?
No, the deuterium species over the non-deuterium species.
The ratio of that.
Yeah.
Yeah, that's known. It's published. Yeah, before. Yeah. I can give you the reference. That's known. Yeah. Now, what's I wouldn't say not study. It's just beginning or not fully understand is the folate right now we're dealing symmetrically. Either you all hydrogen here, all deuterium here, but you could also substitute the one, so become asymmetric, right? And that is not theoretically quite well predicted yet.
So when it comes to searching for the amino acids, are those frequencies well known?
Yeah, it's pretty good because now there is. Let me just see if I have I should say there is a laboratory study on some of those basic amino acids, high resolution data there. Yeah.
In both branched forms and non-branched forms?
Yeah, there's some. Yeah, not very extensive. There's need more manpower to do the laboratory spectroscopy. Yeah.
Do you ever predict lines that aren't seen?
Forget?
Predict lines that are not seen. You showed a lot of spectra, and I think one of the 13 models had a line that wasn't there in the astronomy part.
Yeah. Let me just actually, your eye is quite sharp. But let me just point out. Let me bring this. I think. There is some line we predict not seeing, but that I wouldn't totally believe the detection, because for those complex molecules, so far we don't have a best way to generate a line list, which is 100% fully reliable. I'll tell you the reason for various reasons. First of all, the molecule have a different degeneracy, and there are certain parts you have to do it manually. Okay. When you do manually, you're looking through a data set of, I don't know, we're talking about more than several tens of thousands lines. You often could miss it manually, right? And especially when my colleague says, now we need to go to the high frequency, well, I've got to do this line all over again. So those manual process has to be redone again. So I noticed there's some places agreement there's factor of 2 here. That's due to my manual process. I know that. Okay. There's also, when we predict it, we have to put a certain quantum number region. It's not just frequency cut off, a certain quantum number region. And some we are doing the interpolation, that's okay, it's more reliable, but some we are doing extrapolation because when we do experimentally, we don't get the entire same K or J quantum number for different states. Okay, so the database, the quality is not uniform. That's what I'm trying to say. Yeah.
Very interesting question. Can you expect the entity to measure the parity of DC whenever we detect it?
Parity of
amino acids, like for PC, for example, when I got amino acid.
Well, we haven't even detected yet. Once detected, that's the next question we have to find out. Yeah.
Can we expect to measure the parity in addition to like the abundance of?
Once obtained, I'm sure there's people with look for that such information. Yeah.
Any other questions, comments? If not, before we go upstairs to the cookings, I'll point out we'll be taking Lee home for dinner, so let her know if she'd like to come along. And let's thank her again for
Thank you.